Hey guys, welcome to the third and final video for this part. The objectives for this video are going to be using the distribution of pressure we developed in the previous video to find the net pressure distribution. We're then going to understand how we go from a pressure to a line load, and then we're going to find the force per unit length of our wall, and that's the net force per unit length. So in the previous video we developed the pressure distribution, which looked like this. So the first thing we're going to do is just convert this into a net pressure distribution. So it's very easy to do. We're going to redraw our wall. So we have the points 3 meters, 1 meter. Once again, doesn't have to be to scale or anything, it's very rough. 0.5, 0, minus 0.3, minus 1, and minus 1.5. Okay, so that's our different heights. So all we do now is we look at corresponding points and subtract them from each other. So for example, at 3, left hand side is 0, right hand side is 0. So we're staying at 0. Okay? At the point 1, left hand side is 19.6, right hand side is 0. So we go across to 19.6. Okay, left hand side at 0.5 is we found to be 22.8, and the right hand side is still 0. So we're going to go across at 0.5 to 22.8. A good idea is just to match up these points just so we know where they are. So that corresponds to 1, this corresponds to 0.5. Now at 0, okay, this is where we're going to first actual calculation. At the point 0 we have 25.9 pushing this way, okay, and we have 4.9 pushing this way. So the net pressure will be 25.9 minus 4.9, okay, which gives us 21. So at 0, our pressure, you can see it's starting to decrease now, which makes sense, okay, is 21. At minus 0.3, we have 27.8 from the left and 11.2 from the right, so we're going to go 27.2 minus 11.2. And we'll get 16.6. Okay, at minus 1, we've got 32.2 minus 21.6 will be 10.6. And the final point is 33.6 minus 30 will be 3.6. So we're down to 3.6. Okay, so just matching up these points. Okay, so if we were to draw the net pressure distribution, it would look like this. So this is due to the fact we have two different pressures pushing us in different ways. We're going to get a net pressure distribution. Okay. So at the end of the day, for our question, the main pressure is going against this wall, so it's going to push this wall that way. Okay. This is the net pressure distribution. Now what we want to do is we want to work out the force per unit length. So we want to work out the force. So we now know the pressure distribution, but we want to work out the force distribution going perpendicular, coming normal out the page. So what we're going to be doing is, if we think of this wall as coming out from the page, so think of my pen as an extension of the wall, we're going to be finding the the force per unit length of the wall going into the page. Okay? So we need to understand how we go from a pressure to a force or like a line load. So if I were to just do a very simple example, say we have our wall like this. I'm going to draw it in 3D. Okay, here's our wall. Let's say, just to make it easy, we have a pressure distribution which is nice and simple. Okay, so we're going to make it just like this. So we know our pressure, the unit of pressure is kilonewtons per meter squared, which is kPa. Okay, so we have a pressure distribution. So this is going everywhere. Okay, so everywhere along this area of wall we have a pressure, right? Because a pressure is kPa or kilonewtons per meter squared. That's a kPa. Okay, so it's kilonewtons per meter squared. So it's a force over an area, right? So if we wanted to work out an equivalent line load, say this was 3 kPa. So we have 3 kPa acting everywhere. Okay, and say this length was 2 meters of the wall. If we wanted to work out an equivalent live load, which I'm going to draw in blue to distinguish it, going into the wall, okay, so like this, if we wanted to work out an equivalent live load. You guys might have even seen this before in like structural mechanics or something. So we want to convert this pressure load into a line load going into the page, so going along the wall. All we do is we multiply 3 kPa by 2 meters, so 3 kilonewtons per meter squared, which is a kPa, times 2 meters would be 6 kilonewtons per meter. Okay, so what that's saying is that for every meter we go along our wall, we develop 6 kilonewtons. Okay, so it's a line load of 6 kilonewtons per meter along our wall. Okay, if we were to look at the wall front on, so let's say we're looking at the wall now like this. Okay, there's its depth. What we've done is we've developed, and this is a person standing. Okay, we've developed a line load like this. Okay, so we've converted a pressure, an area load, into a line load. So this was an easy example, but for this example it's very complex. Okay, what we're going to have to do is, just like we did here, we're going to have to find this area. Okay, we're going to have to find that area, and the way we're going to do that is we're going to find this area using the trapezoidal rule. Okay, we're just going to be finding, you can see these are all trapeziums, right? We've got a triangle in the end. Okay, but these are all trapeziums, so we're just going to use the trapezoidal rule, which is very simple to use. It's just going to be the sum. So we know the area of a trapezium is h on 2 outside of a plus b. Okay, so it's going to be the sum of all these trapeziums. Okay, that's all it is. That's the trapezium, the trapezoidal rule to find the area. Okay, just to make this a bit easier, we're going to pop a half out the front. So we're going to find the sum of h outside of a plus b. So that's all it is. So if we were to do our example, okay, try to get this nice for you. So the h is just the different height levels. So this would be one h, that would be another h, that would be another h, and the a's and b's are just the actual pressures. Okay, so for example, the first one, so the force per unit area, so force per unit, sorry, the force per unit length is going to equal, so the force per unit length will equal the sum of this. So we're going to take 1/2 outside of, so our first height is 3 minus 1, so 2 meters, so 2 outside of, now we're going to add 0 plus 19.6, so 0 plus 19.6 plus the next height is 1 minus 0.5, so that distance in there, which is 0.5, so 0.5 outside of 19.6 plus 22.8. Okay, we're finding the area of a trapezium. So 22.8 plus 19.6, either way it doesn't matter. Okay, plus, so the next region is from 0 to 0.5, which is height is still 0.5. Outside of 22.8 plus 21, plus from 0 to 0.3. Okay, so that's going to be a height of 0.3 meters. So 0.3 outside of 21 plus 16.6. Okay, from 0.3 to 1, that length is 0.7. So plus 0.7 outside of 16.6 plus 10.6. Okay, and the last one is from 1 to 1.5, which would be 0.5 outside of 10.6 plus 3.6. Okay, so that's that is going to be the force per unit length. So what we've done is we just found this area. Similarly, how we found this area. Okay, it's just a more complex shape. That's the only thing that's different, and that's going to give us a line load across our wall, a force per unit length. Okay, if we were to work this all out, I've already done it for you guys. You get around 59.9 kilonewtons per meter. Okay, so what this means, if I were to draw our picture, so once again we had a diagram like this. Okay, if I were to draw our wall, so here's our wall. Okay, so this is in 2D, in 3D. So our net force, so it was coming from the left hand side of the wall. Okay, so we're getting a net force like this pushing our wall, right? And this net force we found right now to be, where did I put it? Sorry, 59.9 kilonewtons per meter. Okay, so that is the force per unit length. So this is 49. So we're getting every meter we go across our wall, there's 59.9 kilonewtons of force. So for every meter, for every 1 meter, there's 59.9 kilonewtons of force. Okay, I hope this series helped. Once again, this type of question we just did is, in my opinion, the hardest question you guys could ever get in solid mechanics. So I recommend watching this video 2 or 3 times just to understand all the principles we've just done. And I hope that helps.